Good morning. Start off by logging into Clever for me. Thanks, y'all. All right, so our warm up for today. What is a TV show or a movie that you could watch over and over again? All right, so it is lesson 2 of week 1. We are kind of slowly easing back into the semester. The first lesson was kind of just to get to know us, review what it's going to look like in my class in this semester. Today, we're going to review ionic and covalent bonding because we are going to dive deep into covalent bonding for our next unit. So some reminders. I have to post grades by the 22nd by 3 o'clock. So that's Friday, depending on when you're watching this. So what that means is I have started the process of finalizing and posting grades. That being said, I can accept any some last second mastery assignments because I want you to pass, and I want you to get the grade that you want to get. So if you feel so inclined, please go ahead and try and get that done before I need it Friday morning, so I have enough time to get all of the grades updated. Other reminders, always check assignments, make sure that you're looking on the right spot on our Google Classroom. You might have a bunch of Google Classroom classes right now. Those will be getting archived by Friday. So it will hopefully get a little less confusing, but make sure that you're in our class for this semester too to check on assignments. Edpuzzles, I'm responding to questions or commenting on things, so look for those. Also, let's remember our expectations. So to be safe, responsible, respectful, prepared, and here present students. Thank you all, though, for showing up. It is really important. That's the first step. You're putting in the work. You are here, and you are going to be successful then. So this week, like I said, is really just about getting us back into the swing of things, remembering what the systems and routines look like, and then kind of reviewing and recovering anything that we didn't know or feel great about with ionic and covalent bonding. That's the point of our lesson today. All right, so as for our assignments this week, you had that Edpuzzle preview, like our weekly preview that you get on the first day of the week. There was a short survey that I asked to get a little bit of feedback about how the semester went for you. For a bonus, you could include a screenshot of something that you have uploaded to your backpack. And then today's 2 assignments after this lesson are just to review Edpuzzles about ionic bonding and one about covalent bonding. And so just to make sure that you don't totally feel like clueless and unaware for the assignments, make sure that you watch this first. Let's start out strong. Don't get behind early. Don't get yourself in a hole that you have to dig your way out of for the whole semester. You got this. All right, so we're reviewing ionic and covalent bonding today. All of this is stuff that we have done together in our lessons as well as assignments, but I really want to make sure that we feel good about it. So here is magnesium. I'm going to ask you to identify what would the accurate Bohr model look like, and then finish out by identifying what would the Lewis dot diagram look like. All right, so the protons and the neutrons are 12. We have 12 electrons, so we can have 2 in our first shell. We'd have 8 in our second shell, that get us up to 10, and then 2 in our outside shell. So that means the valence electrons on this buddy are 2. So what our Lewis dot diagram is going to look like is an Mg with 2 dots. All right, now we're doing the same process for oxygen. Show me that you understand what the Bohr model will look like, and then identify what the Lewis dot diagram would be. So you'd have your 8 protons and your 8 neutrons. We'd have 2 electrons in our first shell. We have to get up to 8, so that means we could have 6 in our second shell. That would be our outer shell. The valence electrons would be 6, so our oxygen would have an O with 6 dots around it. So here are our 2 Lewis dot diagrams for these. All right, so now we're trying to think about what type of bond is going to form between these 2 atoms. So some things you might notice right away is how many valence electrons each has. One, you might notice or think about the fact that magnesium is a metal and oxygen is a nonmetal. Well, the way that we fully identify is by looking at their electronegativities. So you're going to tell me what is the electronegativity of magnesium, what is the electronegativity of oxygen. Great. So we found that oxygen's electronegativity is 3.5 and magnesium's is 1.3. So what's the difference there? It is 2.2. So based on that, what type of bond would we have? So the electronegativity is bigger than 1.5, so that means that this is an ionic bond. So here's what this visualization will look like. Those two valence electrons on the magnesium are going to be pulled and taken all the way off and added to this oxygen. What is results then? Results is a positively charged magnesium because it has gotten rid of two negative electrons, and you end up with a negative oxygen ion with a -2 because it gained two negative electrons. So in an ionic bonding, we have the metal giving away or losing its electrons to the nonmetal, the thing with the higher electronegativity. We literally see a transfer of electrons because the electronegativity difference is so big. What is formed are negatively charged anions and positively charged cations that are just attracted to each other because opposites attract. All right, here's another great visualization of a very common bond that would occur between a column 1 or alkali metal family element and a halogen or column 17 family element. So we see that the one electron in the outside shell of the sodium is added to the outside shell, to that open spot on the halogen fluorine in this example, resulting in a positively charged sodium and a negatively charged fluorine that are attracted to each other. There you have it. All right, so now let's think about what would happen if we bonded two oxygens together, because that's how oxygen is actually naturally found. All right, so we've already done the work here. I'm not going to make you draw it out again, but here's what oxygen looks like. And here's what two oxygens would look like. So start to think about, how might these line up and bond with each other? How can they make each other happy? All right. And let's identify what type of bond is going to occur. So it's pretty easy because it's the same element, so you only need to look it up once. But what is the electronegativity of our oxygen? So the electronegativity is 3.5. If we're looking at the electronegativity difference between two of the same thing with the same electronegativity, our electronegativity difference would be 0, right? So if the electronegativity difference is 0 between these two nonmetals, what on the chart defines what type of bond would occur? So this is a nonpolar covalent bond. So the electrons are being shared between the two elements. They each need two. They each have two that they can share with each other. And by doing that, then they meet their octet. So when I count how many electrons each element has, I get to count both of the shared electrons. So I got 2, 4, 6, and 8. I got 2, 4, 6, and 8 around that oxygen. Everyone is happy. This is what is called a double bond. All right, but now let's think about what would happen if I tried to bond hydrogen and oxygen. So let's go through our process to make sure we know what hydrogen will look like. So what is its Bohr model and what is its Lewis dot diagram? So it has 1 proton, 0 neutrons, and 1 electron, just 1 electron in that one shell. Its then Lewis dot diagram will look like this, an H with 1 dot. So if we have our oxygen that needs 2 and 2 hydrogens that each need 1 apiece, let's think about how they're going to maybe bond. So this time, again, we have to look at our electronegativity difference. So we know where oxygen is. Hydrogen is up here in this left corner. Although it is over on the metal side, it is a nonmetal. Don't forget that. All right. So now, what is the difference between our two elements that we are trying to bond? Right, it is 1.4. So let's look at our chart, identify what type of bond would form between oxygen and hydrogen. So the bond would be a polar covalent bond. So what that means is, again, each element is sharing 1 electron or sharing electrons with each other. We can see, again, with these circles, it shows literally where the hydrogen gets to call both of the electrons its. The other one, they get to call both of those with it. And then the hydrogen or the oxygen gets to use its 4 plus those 2 plus those 2 to get up to 8. So what you result with, or what you end up with, if I can move this, maybe, there we go, is this molecule that instead of the electrons being equally shared because the electronegativities are the same, the oxygen's electronegativity is actually big enough that it is kind of starting to pull the electrons towards itself. Now, the difference is not so big that it can snatch them all the way away, but it is pulling it towards itself a little bit. And that's what a polar molecule is. And this particular polar molecule water, H2O, is the one that we are going to be focusing on for the next several weeks. So in covalent bonding, those outer electrons in the valence shells get shared. It's two metals, or two nonmetals, excuse me, and their electronegativities are not so different that there's going to be fully taking the electrons onto themselves. Covalent bonding is really, really cool because that is the major bonding that makes up all of the major molecules and building blocks of life. So if we talk about carbohydrates, we talk about your DNA, we talk about fats, we talk about protein. Those are all massive covalently bonded molecules combining together dozens and dozens and hundreds, sometimes even, of nonmetals connected with these covalent bonds. So some more common examples for you to think about or that you might have seen before. Again, showing and visualizing with you that everyone is being made happy by sharing their electrons with each other. It's kind of cool. So it's important for us to know the key takeaways and the key differences between ionic and covalent bonding. But we are really going to start to hone in and focus on covalent bonding, understanding and visualizing what do molecules look like when they're covalently bonded. And we're even going to build up to start to analyze some of those larger macromolecules. Macro meaning big, molecule meaning molecule. So big molecules that are covalent molecules all held together with these covalent bonds. All right. So I'm curious if you can share with me, how did this review make you feel about ionic and covalent bonding? Are you feeling better? Are you feeling okay? Are you feeling like still terrible? Where are you at? Okay. So there are two more assignments to hopefully, if you're still struggling, to hopefully kind of fill in some gaps for you about ionic and covalent bonds. They are also ed puzzles. So you have the ability to rewatch them. You have the ability to stop and pause. And I really hope that you take advantage and are able to get something from those. So if you don't have any questions, that's it for me. But if you do, please leave one for me and I will respond to it. Thank you all. Have a great rest of your day.